back to the rest of the second practice exam from Alameda. Then we have a couple questions over here, and then we'll see where we're at. So let me get this squared away here. So I believe it's like this doesn't look great. So I think we had gotten up to, that's fine. We'd gotten up to number 4, I think. Yeah, we'd gotten through number 3, right? We definitely did those derivatives. And then we were over here at question number 4. For the following equation, think of y as being locally expressible as a function of x. Oh, that's a lot of words. Use implicit differentiation to calculate dy dx at the point -2, -2. So that's way too many words to this question. It's just a usual implicit differentiation problem, right? They said use implicit differentiation to calculate the derivative when xy is equal to -2, -2. So the first step is going to be to differentiate both sides. And since we're being asked to find the derivative at a particular point, our second step is to immediately, after differentiating, plug in x equal to -2 and y equal to -2. And then lastly, we'll solve for the derivative. All right, so let's take our equation here. X squared plus xy minus y squared equal to 4. And we're going to differentiate everything, or take the derivative of everything with respect to x. The derivative of x squared is just 2x. The derivative of x times y requires the product rule. So it's the derivative of x, which is 1, times the not derivative of y, which is y, plus the not derivative of x times the derivative of y, which is the derivative of y. That one always seems to throw people off a little bit, but the derivative of y is literally just dy dx, the derivative of y with respect to x. You can also write y prime if that's your preference. Either way, dy dx or y prime, or some other crazy notation. Minus, we have some stuff squared. The derivative of some stuff squared is 2 times our stuff to the first times the derivative of our stuff. So 2 times y to the first times dy dx. Equal to, don't write 4, it's 0. Right? The derivative of 4 is 0. For some reason, I've seen it way too many times with the constant over there. People forget that also you're taking the derivative of and just leave it as whatever. No, the derivative, you have to take with the derivative of whatever's on the right-hand side, whether it's a constant or whether it's in functions of x and y. Okay. Now, since we're in this nice situation where we are given a point to find the slope of the tangent line or the derivative, we just plug in the point. So this was our first step here, differentiating both sides. And then our second step is going to be plug in -2 for x and -2 for y. So we're going to plug in x equal to -2, y equal to -2. So we're going to get 2 times -2 plus 1 times -2 plus -2 times dy dx minus 2 times -2 times dy dx equal to 0. Now, if it were me as a student doing this, I probably wouldn't write this much. I probably would have skipped this step and said, I know that 2 times -2 is -4, and 1 times -2 is -2. And I've got -2 times dy dx plus 4 times dy dx. I think that's a totally reasonable first step when you plug in here. And then we're going to combine our dy dx's. I have a -2 dy dx plus 4 dy dx. That's going to be a positive 2 times dy dx. And over here, -4 minus 2 is -6. So -6 plus 2 times dy dx still equals 0. We're going to add 6 to both sides. So we're going to get 2 dy dx equal to 6. Finally, divide both sides by 2 to get dy dx equal to 3. So the answer is 3. Sorry. I might feel compelled to write dy dx equals 3, but you shouldn't actually have to write that. The answer is just 3. And actually, write this, you should probably write dy dx evaluated at -2, -2 is equal to 3. It's probably the more correct thing to write there. Questions about this implicit differentiation problem? Follow-up. What if the problem had just said to find dy dx and not to plug in -2, -2? Well, then, if we were just finding dy dx, at this point here, we then would have done the algebra to solve for dy dx. So we would have grouped all the dy dx things on one side. So let's bring them, I don't know, let's bring them all to the right just for a change. So I have 2x plus y on the left, and on the right-hand side, I have -x times dy dx plus a 2y times dy dx. And then we're going to factor out the dy dx. That's why we're taking the step of bringing all the dy dx things to one side. So I factor out the dy dx. I'm left with a -x plus a 2y. It would be just as fine to write 2y minus x. And then finally, divide by that to get 2x plus y divided by -x plus 2y equal to dy dx. And I'll point out that if you did it this way first, and then plugged in your point, -2, -2, it should still work out. dy dx evaluated at -2, -2 is going to equal 2 times -2 plus -2 divided by -2 plus 2 times -2. That's going to equal -4 plus -2 is -6 divided by 2 minus 4 is -2, and that is still +3. I wouldn't do it this way, but if the question was just to take the derivative, then you would do this usual work here. There's something I wanted to say here. Oh, I'll just mention here. This kind of, I was looking at this, I was like, oh, that feels like it looks like you could simplify. No, you cannot simplify this. It does not simplify. There's no good simplifying that happens over here. And that's almost, with rare exception, always true when you find a derivative implicitly. It's that you usually cannot simplify it. There's a couple special exceptions, but they're special. All right, continuing along. Look at problem number 5 here. I really should find, oh, there we go. There we go. Should find my single-sided pieces of paper. There we go, much better. Problem 5. Suppose the functions f, g, and h are differentiable functions of the variable t and are related by the equation f of t squared plus g of t squared equals h of t squared. Additionally, suppose all this stuff. F of 2 is 4, h of 2 is 5, f prime of 2 is -1, h prime of 2 is 3, and g of 2 is positive. Interesting. Okay. So they're asking us to find g prime of 2, which means we should take the derivative of everything first. We shouldn't try to solve for g, or that's not, if g was solved before, we would do that, but a square root here is an issue. So we should just differentiate both sides implicitly, just like we did before. And it's written kind of very nicely. So if we think about having f of t squared plus g of t squared equals h of t squared. It's looking very Pythagorean theorem-y, not that that really matters. We're just going to take the derivative of both sides, differentiate. And just like before, the derivative of something squared is 2 times that thing to the first power times the derivative of the stuff. Exactly. So we're going to get 2 times f of t to the first times f prime of t plus 2 times g of t to the first times g prime of t. I didn't need to write the first power there, but I did. Equals 2 times h of t to the first times h prime of t. And we're trying to find g prime of 2. So I guess what I'm going to do now is just plug in 2 for t. But I can't just do it for one t. I have to do it for every t. I will say let's do 2 things at once. Let's not do 2 things at once. Let's divide everything by 2. Right? We don't need this 2, this 2, and this 2. If we divide both sides by 2, that's a totally legit thing to do. So we can say we just have f of t times f prime of t plus g of t times g prime of t equals h of t times h prime of t. And now let's plug in 2 for t, meaning you have to plug in 2 for every t. So f of 2 times f prime of 2 plus g of 2 times g prime of 2 equals h of 2 times h prime of 2. I might have picked a different number just because t and 2 often get kind of flipped in my mind somehow. Like, I just don't like the choice. I would pick like 3 or 5 or something else, but oh well, doesn't matter. Okay, we're trying to figure out what this is, which means we probably can plug in something for everything else. Let's look at our list here. F of 2 is 4, so we're going to rewrite this as 4 times f prime of 2 is -1 plus g of 2 is positive. Interesting. Okay. So I don't know what that's going to be yet. Interesting. And g prime of 2 is what we're trying to figure out. A little worried. Oh, well. H of 2 is 5. H prime of 2 is 3. So I have that. Oh, interesting. Ah, that's tricky. I was like, I'm not sure how we're going to do this here. So, but continuing on this way, pretending like I don't know what I'm doing, I'm going to say, well, that's a -4. So I'm going to add 4 to both sides. So 5 times 3 is 15 plus 4 is 19. So I have that g of 2 times g prime of 2 equals 15 plus 4, which is 19. So then I should be able to say that g prime of 2 is equal to 19 to, oh, sorry, yeah, g prime of 2 is equal to 19 divided by g of 2. G of 2. Oh, wait, we have an equation up here. Right, we can say that f of 2 squared. I was wondering why they told me g of 2 is greater than 0. And I should have been more thoughtful about them. Like, oh, I'm going to need to use that to find something. And then when I was like, I'm not finding g of 2, that should have been the moment I was like, oh, I probably need to use the fact that g of 2 is positive. And it is, right? F of 2 squared plus g of 2 squared equals h of 2 squared. But we know that f of 2 is 4, so we have 4 squared. We're trying to find g of 2 squared. And it's probably going to equal 5 squared. Yep, it sure is. So 4 squared plus 3 squared equals 5 squared. Or you could just solve it, right? G of 2 squared is equal to 25 minus 16, which is 9. And this is why we need to know the g of 2 is positive. Because the solutions here are the g of 2 is positive 3 or -3. So we're going to say, oh, wait, g of 2 is plus or minus 3, but it's positive 3 specifically. Yeah. Right. Oh, from this step to this step, I just divided both sides by 2. Just to make our lives easier. I didn't need to write all those 2's every time. So then we can say, oh, great, that's going to be equal to 19 divided by 3. That's it. It's a good question. I like that. It's smart. It's not like too terrible, but it makes you think about what you're doing. Questions about this? I will just point out that when we were doing the previous problem, I was exactly thinking of y squared as like f of t squared. And the derivative of f of t squared was 2 times f of t times f prime of t. Or 2 times my function times the derivative of my function. We'll keep things in order here. What else do we have? Problem 6. Ooh, problem 6. All right. Lots of words. You can't see them yet. Okay, there we go. So let's read this, and as we go, write down what's important. A fungus grows in the form of expanding circle. Okay, we've got a circle. We'll probably, I mean, sure, you could draw a circle, I guess. Let A of t be the area of the circle after t hours, and R of t be the radius of the circle after t hours. Then A of t and R of t are related by the equation A of t equals pi times R of t squared. Great. You kind of already knew that. Usually we don't write it with the t's, but totally fine to write it with the t's. Suppose the radius is increasing at a constant rate of 3 millimeters per hour. So we know that you can either write this as dr dt or r prime of t is equal to 3 millimeters per hour. Either notation is fine here. Usually I would just stick with the dr dt notation, but since we're writing our functions this way, it might feel nicer to use r prime of t. But they both mean the same thing. They both just mean the derivative. It just means the rate of change of the radius as time goes on. How fast is the area of the circle increasing when the radius is 7 millimeters? So we're asking, what is the rate of change of the area or a prime of t equal to when the radius is 7 millimeters. And I want to point out that this problem and the previous two problems have a very common theme, which is that you're going to take the derivative of both sides and you're going to use implicit differentiation, or essentially, or the chain rule, kind of the same thing. And then in each of these three problems, we're going to differentiate first and then plug in the point of interest. But you're always having to take the derivative first and then plug in whatever your point is to figure out what's going on where. Same deal here. So we're going to take the derivative of both sides. I might as well use the prime notation because it feels convenient here. If we differentiate both sides, we're going to get a prime of t on the left. On the right-hand side, the pi hangs out. And the derivative of r of t squared is 2 times your function times the derivative of your function. It's kind of close there. And now we're going to plug in 7. So we're trying to find this. So I'm going to write a prime of 7, but I'm not, that's going to end up equaling whatever we actually get here. That's going to be 2 pi times r of 7 times r prime of 7. Okay, this is a little funky. R of 7. So I feel like this question is not excellently written. No, that's all right. I take it back. It's fine. Yeah. No, I take it back again. It's not that fine. It's fine, but you have to make an assumption, which is pretty standard. So they're telling us that the radius is increasing at a constant rate of 3 millimeters per hour. And then they ask us, how fast is the area of the circle increasing? I made a mistake. Right, the time isn't 7, the radius is 7. I should not be plugging in 7 for t here. What I really should be writing is that my rate of change, a prime of t, is going to equal 2 times pi times my radius, not r of 7, just 7. And my rate of change of my radius, which is 3. I will point out, I don't think you should write the units yet, but if you did, that 7 would be measured in millimeters. This 3 would be measured in millimeters per hour. And so your units here would be millimeters squared per hour, which it should be if it's the rate of change of an area. So we're going to end up with 2 times 3 times 7, which is 42 pi square millimeters per hour. And I do think for related rates problems like this, you should default to including the units in your answer. And you should just be able to figure them out by thinking about what kind of thing, length, area, or volume we have that is changing, right? If it had been a volume, it would have been millimeters cubed for whatever the unit of time is, hours in this case. So take whatever your units of length are, take whatever your units of time are. Is it a length, area, or a volume? If it's a length, it's your units per time. If it's an area, it's your units squared per time. And if it's a volume, it's your units cubed per time. Whatever your length units and time units are. But there's a lot of options, right? I mean, there's time, seconds, minutes, hours, days, weeks, years, decades, millions of years, right? Length as well, right? There's lots of different measurements of length, but hopefully they're not doing something. No, I wouldn't say that. No one's going to be like giving you one kind of unit, making you change it to another kind of unit on test. I hope that'd be terrible. Yes.
Question about the previous chart.
Sure. Sure. So that 3 came from the fact that g of 2. So we were able to get that g of 2 times g prime of 2 is equal to 19. And then we said that g prime of 2 is equal to 19 divided by g of 2. And then we went back and said, oh, wait, we know that f of 2 squared plus g of 2 squared equals h of 2 squared, because we're given this equation that f of t squared plus g of t squared equals h of t squared for any value of t. But then we know that f of 2 is equal to 4. So what we really have is 4 squared plus g of 2 squared equals, and we're given that h of 2 is equal to 5 squared. So we're given that 4 squared plus this thing squared equals 5 squared, or in other words, that g of 2 squared is equal to 25 minus 16, which is 9. And then g of 2 could be plus or minus 3, but they told us g of 2 was positive, so g of 2 has to be 3. That's where that 3 is coming from. Which is pretty typical for these like related rates problems or implicit differentiation problems, is that, especially more related rates really, is that once you've done your differentiating of both sides and you're plugging in all the rates you know and all the things you know, sometimes you have to go back and solve for one of the things you're supposed to know based on the original equation they gave you. Cool. I think that's the end of his practice test. Yes, it is. Okay. Right on. Yeah, that's another thing there. There's some paper. People have some questions about things. Too much paper probably, but that's fine. So some questions people had. That's so many words. Okay. I'm going to read the words. I'm not going to write them down. I'll write down the pertinent things here. So here are the words. Scientists can determine the age of ancient objects by the method of radiometric dating. Okay. I should just ignore all that because it doesn't tell me anything I need to know yet. The bombardment of the upper atmosphere by cosmic rays converts nitrogen into a radioactive isotope of carbon-14 with, okay, here's something actually important, a half-life of about 5,730 years. So we know that carbon-14 half-life is 5,730 years. Okay. Vegetation absorbs carbon dioxide through the atmosphere, and animal life assimilates carbon-14 through food chains. When a plant or animal dies, it stops. So you should just be looking at this and be like, okay, words. And then it stops. So when a plant or animal dies, stops replacing its carbon, and the amount of carbon-14 begins to decrease through radioactive decay. So we know that we have like a radioactive decay model, which we aren't surprised by at all. Therefore, the level of radioactivity must also decay exponentially. Okay, here's finally the question. A discovery revealed a parchment fragment that had about 84% as much carbon-14 radioactivity as does plant material on the Earth today. Estimate the age of the parchment. So our parchment has 84% of the carbon-14 as a living thing. How old is it? And just like every single time we've had a radioactive, or sorry, an exponential growth or an exponential decay problem, I'm going to recommend to draw a little table like this with times and amounts. And yeah, how many? There's some, yeah. And typically, when I do a problem like this, I like to think of time equal to 0 as the time when things start, where I have kind of all the stuff. Now, this one's a little bit atypical, but not really, in that you aren't given any amounts, right? You usually be like, oh, time 0, you have 50 grams. Time later, you have this many grams, whatever. Here, I think we're in a better situation. Because if they don't give you an amount, you can make it up. And I'm going to pick the nicest number there is to take percentages of. 100. Grams, pounds, kilograms, whatever you like. Or you just say 100 and not even have a unit on there, which is probably the best choice, actually. And then we know that 5,730 years later, a whole half-life, we're going to have how many grams? Right, half of what we said we started with. In fact, let's kill the grams there and just say it's 150. And then we are trying to figure out how long it takes until we get to a point of having 84% of what we started with, and 84% of 100 is 84. Why we picked 100 in the first place. So if you're ever doing a problem like this where you're just given percentages, do yourself a favor and say you're starting off with 100. 100% if you like. Okay, the process is typical from here on out. We write our model here. We plug in each data point. I always feel like you can skip this step, but if you want to plug this in, you can say, great, 100 equals CE to the K times 0, just plugging in 100 for Y and 0 for T. And K times 0 is 0, e to the 0 is 1. So you end up just getting that 100 is equal to C, which is always the value of C you're going to get, is what I should say. The value of C you're always going to get is whatever the amount is at time 0. And then we take the next data point and you plug that into your newly refined model. So we did have y equal to now 100 e to the kt, and we're going to plug in y equal to 50 and t equal to 5,730. There's still a k there, James. And then you solve for k. And you might be familiar with the fact that when you solve for that k and you have a half-life, you always end up getting the natural log of 1/2 divided by how long the half-life is. You should still show the work, but you should know that that's what you're going to get. Divide both sides by 100. Oh yeah, 50 divided by 100 is going to turn into a half equals e to the 5,730 times k. Take the natural log of both sides. The natural log of 1/2 or 0.5 is equal to the natural log of all this, but the natural log of e to the something is just the something. And then divide by 5,730 to get the natural log of 1/2 over 5,730 is equal to k. So now we have our fully fledged model of exponential decay. Y at time t is equal to 100 e to the natural log of 1/2 over 5,730 times t. It's kind of tiny there. Let me zoom in a bit. And now we finally can answer the question. How long does it take till we get to 84%? So we're going to set y equal to 84 and solve for t. So 84 equal to 100 e to the natural log of 1/2 over 5,730 times t. Same process essentially as we just used for solving for k. Divide both sides by the coefficient of e, take the natural log of both sides, isolate the variable. So here, instead of writing 84 divided by 100, let's write 0.84, right? 84% has a decimal, 0.84. Not a surprise. 0.84 is going to equal e to the, all that stuff, e to the natural log of 1/2 over 5,730 times t. Take the natural log of both sides. You're going to say that the natural log of 0.84 is equal to the natural log of e to all that junk is just all that junk. Natural log of 1/2 over 5,730 times t. And finally, multiply both sides by 5,730 and divide both sides by the natural log of 1/2 to get 5,730 times the natural log of 0.84 divided by the natural log of 1/2. On an exam, if you don't have a calculator, that's all you can do. I know it's still a lot, but like you can't go any further. And that's how old the thing would be. So I guess if you had a calculator, which I suppose I do. Quick logic check here. Should this thing be older than, or should this thing be older than 5,730 years or less old than 5,730 years? Less old, right? Because it hasn't gotten down to 50% of what you started with. So we haven't had enough time to get there. Let's double check though and see what it is. You can kind of see that maybe, kind of, sure, yeah, all right. So we've got 5,730 times the natural log of 0.84 divided by the natural log of 0.5. 1,441 years. So we would say that our parchment is approximately 1,441 years old. Okay. Seems not unreasonable. Questions about that? It's a pretty, so I just want to point out for the exponential growth and decay problems, the process is pretty standard, right? You're almost always going to have two different data points with a time and an amount and a time and an amount. You're going to plug each of those in to find your C and your K. And then after you've found your C and your K, you're going to have your brand new model with all the C's and the K's plugged in. And then you're going to find the other thing you're looking for by plugging in the thing you know and solving for the thing you don't know. The same kind of 5 steps every time, or however many steps it is. I don't know. It feels like a lot of steps. Okay. Let's look at what else is on here. Oh yeah, some of these things. Cool, I like these. Yes. Make sure I'm putting things in the right order here. Okay. We'll change this one up just a tiny bit. So you want to find the derivative of or differentiate. This is written in a nice way. Y equal to x squared plus 6 to the secant of x power. Change it up a tiny bit. Okay, so when I see something like this, where I have something that's vaguely exponential, the exponential is not really the right word because we have variables in the base and the exponent. There should be a really big red flag here that's telling me I need to use logarithmic differentiation. If you've got variables in your base and in your exponent, we have to use logarithmic differentiation. There's really no other way. So the first step is to take the natural log of both sides. The natural log of y equals the natural log of x squared plus 6 to the power of secant of x. The reason we've done that is so that we can get that secant of x out of the exponent. I want to bring that down in front using those log rules. So we're going to rewrite this as the natural log of y equals secant of x times the natural log of x squared plus 6. After that, we're going to differentiate both sides. On the left side, you're almost always going to have the natural log of y, and you're going to differentiate that implicitly, and you're always going to get 1 over your stuff times the derivative of your stuff. On the right side, product rule. You have a function of x times a function of x. So we're going to do the derivative of secant, which is secant of x times tangent of x, times the other function left alone, plus, then you switch it up and you leave the secant of x alone, and you multiply by the derivative of the natural log of x squared plus 6, which is 1 over x squared plus 6, times the derivative of x squared plus 6, which is 2x. Then we're going to solve for y prime, which I think could be a one-step process, but it's totally fine to make it a two-step process. Excuse me. The first step is to multiply both sides by y to get y prime equal to y times all this. This is probably your moment to, if you wanted to simplify this a little bit, you could. It doesn't really simplify very well though. You have secant of x times tangent of x times the natural log of x squared plus 6. Plus, you could rewrite this as 2x times secant of x all over x squared plus 6. If you really wanted to, you could factor out a secant, but there's really no value added there. Finally, and again, I think you could have skipped this step and jumped straight to saying that y prime is equal to, plug back in what y was equal to for y. So it's going to be x squared plus 6 raised to the power of secant of x multiplied by all of that. Secant of x times tangent of x times the natural log of x squared plus 6 plus 2x times secant of x all divided by x squared plus 6. Yeah.
When on base.
So I would say there's two occasions when you use it. When you have something that's like a power exponential, where both the base and the exponent have a variable, or you're told to. So someone might give you something where you do not need to use it explicitly, but they have said use logarithmic differentiation. That's somewhat atypical. There's certainly textbook problems like that where you have a function where you could just differentiate it kind of regularly, but they've said use logarithmic differentiation instead. Yeah.
1 over x squared plus 6.
Times 2x. So whenever we take the derivative of the natural log of some stuff, of any stuff, so the derivative of the natural log of some function of x is always going to be 1 over that stuff multiplied by the derivative of that stuff. It's just the application of the chain rule, really. Because more basically, the derivative of just natural log of x is 1 over x. So we're just replacing the x with some stuff, but we know that when you replace the x with stuff, We always have to multiply by derivative of the stuff. We've only said it like 1,000 times in class. Not to harp on you, just I'm saying in general to everybody, right? You know it's the derivative of the stuff because we said it a bajillion times in class. So why don't you all try, not that one. Why don't you try doing one like this? Find the derivative of y equal to x plus 7 to the power of tangent of x using the same process. I'll give you a few minutes to do that. Sure. We'll talk about that in a second. All right, let's take a look. So, sure. Start by taking the natural log of both sides. I'll point out, if someone is writing a test and they're cruel, they might write it as take the derivative of, they might write it like this. Cruel is maybe an oversell, but if they were not feeling particularly generous, they might write it as find d dx of x plus 7 to the tangent of x power. You have to recognize at this point that you have a base and an exponent that have a variable. And before you can do this process here, you have to write y equals your function so that you can take the natural log of both sides of that equation. Usually most people at this point are writing as y equals, but just in case they aren't, be aware. So you take the natural log of both sides, then we bring down the power, and then we differentiate both sides. And again, it's almost always going to work out that on the left-hand side, you have 1 over y times y prime. On the right-hand side, you're going to have to use the product rule. Derivative tangent is secant squared of x. Leave the other piece alone. Plus, now you leave the tangent of x alone. And the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is just 1 in this case. But still good to be thinking about the chain rule, even when the stuff is pretty straightforward. Okay, let's skip the intermediate step here and jump straight to saying that y prime is equal to y, which is x plus 7 to the tangent of x power. And that's just my y. I'm just replacing it. Times all this jazz over here. Secant squared of x times natural log of x plus 7 plus, I would probably write this as tangent of x divided by x plus 7. And that's our final answer. there's one more like this, but let's address that other question here, which is, what about the derivative of tangent squared? Right, tangent squared, secant squared. Okay, either one, yeah. I mean, either way, sure. They're all kind of the same. So if you're trying to find the derivative of any trigonometric function to a power, it's going to be in your best interest to rewrite it as your trigonometric function in brackets raised to that power. Because then I think it's more obvious that, oh, I have some stuff to the third power. And I know the derivative of x cubed is 3x squared. So the derivative of some stuff cubed is 3 times my stuff squared. But then what do I have to multiply by? The derivative of the stuff, which in this case is secant of x times tangent of x. And if you were told not to simplify, you should stop. Even if it's really, really tempting to say secant squared times secant is another secant cubed. But then if you did want to simplify, it would simplify as 3 times secant cubed of x times tangent of x. Okay, so secant squared times another secant. All right, why don't you all try this one? Find the derivative of tangent to the 6th power. Good. All right, it's the same idea. You're going to rewrite this as the derivative of tangent of x raised to the 6th power. And then you have some stuff to the 6th, so your derivative is going to be 6 times your stuff to the 5th power times the derivative of that stuff, which is secant squared of x. And if you really felt compelled to, you could rewrite it as 6 times tangent to the 5th of x, which is just an abbreviation of that, times secant squared of x. Yeah. So why don't you guys try, I was just about to give you a harder one. Why don't you try taking the derivative of sine to the 4th of 3x squared plus 5x. And again, I would highly, highly, highly recommend rewriting it first. All right. You're rewriting the derivative of sine to the 4th of 3x squared plus 5x as the derivative of sine of 3x squared plus 5x all raised to the 4th power. So I'm seeing this as, oh, I've got some stuff to the 4th. And as is usual, my derivative is going to be 4 times my stuff. We leave the stuff alone. We don't change it yet. Raised to the 3rd power, but then we have to multiply by the derivative of all that stuff. That's going to require the chain rule again, because inside there we have sine of some new stuff. And the derivative of sine of x is cosine of x. The derivative of sine of some new stuff is going to be cosine of our new stuff times the derivative of our new stuff. And the derivative of that new stuff is straightforward. It doesn't require the chain rule. We know the derivative of 3x squared plus 5x is 6x plus 5. And if I write it like that, I'm going to lose at least a point. Because what I've done there is I've said I have 4 times this cubed times cosine of this times 6x. And then add 5 after that. But it shouldn't be like that. It should be cosine of this stuff times the entire derivative of that stuff. So it's super duper important whenever you're multiplying by the derivative of the stuff that the entirety of the derivative of the stuff is in parentheses that you're getting multiplied by. Cool. Okay, there was another logarithm differentiation question that I did want to go over, because it actually offers something kind of unique here. So what do we want to find or differentiate y equal to the 5th root of x raised to the power of x plus 2. What I want to point out here is there's actually a couple ways you could go about doing this, and you should be able to get to the same place either way. Let me show you what I mean. So if it were me, I would probably start by actually simplifying this first. Here's what I mean. You can rewrite this as y equal to x to the 1/5 to the power of x plus 2. But then when you have a power to a power, you can multiply the powers. So we can really rewrite this as y equal to x to the power of 1/5 times x plus 2. And then if we take the natural log of both sides, look what happens. You get the natural log of y equal to the natural log of x to the 1/5 times x plus 2. And then we bring the entire power down. And so we end up with the natural log of y equal to 1/5 times x plus 2 times the natural log of x. What I really want to point out, though, is if you didn't do the simplification first, you should still be able to get to the same place. So here's what I mean. If we just left it like this and took the natural log of both sides. So we did the natural log of y equal to the natural log of the 5th root of x to the x plus 2 power. First, we're going to bring down the power, the x plus 2. So we're going to have the natural log of y equal to x plus 2, parentheses are important here, times the natural log of, let's rewrite the 5th root of x as x to the 1/5 power. But then we still have the natural log of something to a power. And as far as the logarithmic rules are concerned, we can bring down that power too. So we can rewrite this again as the natural log of y equals 1/5 times x plus 2 times the natural log of x. Same thing we have right there. So either way you want to do it should be fine. You should do whatever makes more sense to you. I certainly thought of it this way first, but then when I rethought about it, I was like, oh, well, this probably is actually easier to not think about doing it that way first. So whatever floats your boat. Let's see here. So then we're going to differentiate both sides. As is usual, the derivative of the natural log of y is 1 over your stuff times the derivative of your stuff. And as is typical, on the right-hand side, you're going to get the product rule. Let's think of it as the product of this piece times this piece. The derivative of 1/5 times x plus 2 is just 1/5. And then we're leaving the natural log of x alone. And then we're going to leave the 1/5 times x plus 2 alone and multiply by the derivative of the natural log of x, which is 1 over x. Finally, we're going to multiply both sides by y. Let me just write it down here. So we're going to get that y prime is equal to y times all that stuff. 1/5 natural log of x plus 1/5 x plus 2 times x. And the y here is going to be the original y I started with, which is the 5th root of x raised to the power of x plus 2. Not too terrible. Those are all the things people had explicitly asked. I can certainly start doing other things, but if anyone has specific questions they would like me to address, yeah. E to the y cosine of x equals 1 plus sine of x y. Okay. Sound right? Is that the right equation? Okay, yeah. So if you saw this question and nobody gave you any instructions, what would you imagine you were supposed to do? Use what kind of method? Right, it's clearly an implicit differentiation problem, right? You got x's and y's mixed up together. When you see that, you're like, oh yeah, I'm using implicit. Now, maybe it's an implicit problem where we're trying to find dy dx or y prime, or maybe it's an implicit problem where we're trying to find the derivative at a particular point. I think it's just a dy dx one, but when you see something like this, you'd be like, okay, I'm thinking implicit differentiation. So now we're going to solve, we're going to find dy dx or y prime, whatever you like to call it. So we're going to differentiate both sides. On this left side here, we have to use the product rule. When we differentiate, the derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff times the other function left alone. In fact, let's be a little more explicit here. I'm thinking of this as my f, this is my g. So over here, I'm getting f prime times g, and then I'm going to switch it up. I'm going to leave the f alone, e to the y, and then we'll talk about the derivative of g, the derivative cosine. Now be careful here. If you write this, you're going to end up having potentially problems because you might mix it up in your mind and think that you have e to the y minus sine of x. We don't. We have e to the y times negative sine of x. So I think it's super important that when you have something times something that happens to have a negative in front of it, that we put parentheses around that negative sine of x. And then in the next step, I'd probably put that negative out in front of the e to the y. Because something times a negative something just ends up being negative overall. That's my f times g prime. On the right-hand side, the derivative of 1 is 0. The derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. The derivative of x times y also requires the product rule. The derivative of, I feel like, is this right? I feel like it was, is it sine of xy? Not sine of x times sine of y? Okay, so the derivative here is going to be 1 times y plus x times y prime. After we've differentiated both sides, our job is typically to try to isolate y prime, but often, especially like right over here, if you have a parentheses that has a y prime added to a thing that doesn't have y prime, that almost always means you have to distribute this to each of those terms before you can start isolating the y primes. So we're going to rewrite this kind of terribly as e to the y times dy. Sorry, and I apologize. I used y prime here and dy dx over here. That's terrible. Let's call this dy dx over here. Sorry about that. That's unexcusable. It's really the same thing, but you should be consistent with your notation. So sorry about that. So we have e to the y times dy dx times cosine of x. I'm writing this part here as minus e to the y times sine of x equal to cosine of xy times y plus cosine of xy times x times dy dx. And then now we can group together the terms that have a dy dx. Question. Because it's plus a positive thing times a negative thing. So I just made the choice to say I'm going to write, instead of writing like, plus 5 times negative 2, we can just write that as minus 5 times 2 or minus 10. So let's group all the y prime or dy dx things together on the left. So we're going to have e to the y times dy dx times cosine of x, bless you, minus, bless you again, cosine of xy times x times dy dx. So those are the red things. And then on the other side, we want all the not dy dx things. So we want that and that. So it's gonna be, I'm going to rewrite this as typically you write stuff like before the trig function usually. So instead of writing cosine of xy times y, I'm going to write y times cosine of xy, and then plus e to the y times sine of x. I will point out, after you differentiate both sides, the rest of this is just a lot of careful, painstaking bookkeeping. Right? You just have to pay attention to where all the things end up. You have to be really you have to be a bit meticulous about it, right? I'm writing a lot here, but I think it's important to write down all the stuff each time, not just the stuff that's changing, but really in each step of this process, you should be writing down as much as I am. Not any less, really, at all, for real. Like you should write down the whole thing every time. So then on the left-hand side, I'm going to factor out the dy dx here. So that I have now dy dx times the leftovers, which is e to the y times cosine of x minus, I'm going to write this as x times cosine of xy. You might be able to convince me that this one step, you don't have to write the right-hand side. I'm still going to write it. Y times cosine of xy plus e to the y times sine of x. Finally, divide both sides by this and get that dy dx is equal to all this stuff, y times cosine of xy plus e to the y times sine of x, divided by all that stuff, e to the y times cosine of x minus x times cosine of xy. Whew, that's gnarly. Does that look right? I mean, I think it's right. Yeah, it's a lot to keep track of that. See. What else? So I know we have 3 different classes here. Some people are not covering chapter 4 on their exam, right? No, yes, that is true, or no, that's not true. Yes, that is true. But I think Lewis's class is covering the first couple sections of chapter 4. Okay. Kind of makes it hard for everybody though. Why'd it have to be all different? Not you guys, him specifically, not people in this class. You're fine. Well, let's do a linearization. Yeah, let's do a linearization. Let's do a fun one. You guys like fun. What are you talking about? Use a linearization to, which one do I like here? Yeah, to estimate tangent of 44 degrees. Classic problem. You're welcome. So, a couple things here. First of all, let's identify the function. So our function is just the thing you're trying to figure out, but replace the number with the letter x. So our function here is tangent of x. We also know that we're going to need the derivative, right? That's always true when you're doing a linearization. So let's go ahead and write it down. F prime of x is going to be secant squared of x. And then we need to find the a value. The thing we're going to plug in that's easy to do, that's close to the number that's already in there. So what's an angle that's close to 44 degrees that's easy to take tangent and secant and sine and cosine of? 45 degrees, exactly. A is going to be 45 degrees. It usually should be relatively obvious what your A should be. So then we also know that tangent of 45 degrees is going to be 1. And secant of 45 degrees is the square root of 2. So secant squared of 45 degrees should be the square root of 2 squared, which is 2. If that is unclear to you, let me show you the triangle where that's coming from. So here's your classic 45, 45, 90 right triangle, where you can make the legs any lengths you want that are the same. The standard choice is 1 and 1. Because they have to be the same because it's an isosceles triangle. And then we can find that third side, using the Pythagorean theorem. 1 squared plus 1 squared equals c squared. 2 is equal to c squared. C is equal to the square root of 2. Tangent of 45 degrees is the opposite over adjacent, which is 1 over 1, which is 1. And I don't remember secant very well, but I do know that secant is the reciprocal of cosine. Cosine of 45 degrees is the adjacent over the hypotenuse, which is 1 over root 2. So secant of 45 degrees is the reciprocal of that, which is root 2 over 1, which is root 2. And then secant squared is the square root of 2 squared, which is 2. Cool. So now the linearization. I think it's worth writing down the formula that L of x equals f of a plus f prime of a times x minus a. I'll remind you again, because I think it's important. This is just the equation of the tangent line. Sorry, tangent line, not like the function tangent here. Like, it wouldn't matter if this was x cubed. It's still the equation of the tangent line. Right? This is really just a fancy way of writing y minus y1 equals your slope times x minus x1, and then solving for y. Y equals y1 plus your slope times x minus x1. You've seen this equation many, many times. You know it well. So in this case, it's going to be y, L of x, equals my y value, which is just what you get when you plug in 45 degrees to tangent. So right here, right, there's my f of a, which is going to be 1, plus my f prime of a, which is going to be that, times x minus my a, and my a was 45. Okay. I'm making an on-purpose mistake here that I will correct in a moment. But I want to make this mistake so that you all see, so because people like to ask this kind of question to get people to make this kind of mistake. So the value I was trying to estimate here was tangent of 44, right? So I'm going to say, great, I'm going to plug in 44. I'm going to say the tangent of 44 is approximately L of 44, which is 1 plus 2 times 44 minus 45, which is going to be 1 plus 2 times -1 is -2 plus 1 is -1. Here's why I'm saying this kind of questioningly. Tangent of 45 degrees is 1. Tangent of 44 degrees should be pretty close to 1. It should definitely not be -1, right? Tangent 44 degrees is in quadrant 1, where tangent is for sure positive. If tangent was negative, our angle would have to be like bigger than 90 degrees, or all the way to like 300 degrees, like between 270 and 360. So it's really suspect that we're getting a negative number for tangent here. And the issue here is that, and I made an on-purpose mistake, is that we have to be working in degrees here. Those should be degrees. So the tangent of 44 degrees is approximately 1 plus 2 times -1 degrees. Or 1 minus 2 degrees. But the problem is you can't subtract degree numbers from regular numbers, but you can subtract radian numbers from regular numbers. So you have to change these degrees to radians by multiplying by pi over 180 degrees. So you end up getting something like 1 minus 2 pi over 180, which is pi over 90. Or if you prefer, I don't really prefer, but if you prefer 90 minus pi all over 90. And if you actually just to use a calculator to see, I mean, you can kind of already see that's going to be pretty close to 1, because it's a number that's almost 90 over 90. But if you actually want to use a calculator, it's 90 minus pi divided by 90 is about 0.965. A much more reasonable answer, considering the tangent of 45 degrees was equal to 1. So when people do a linearization, specifically for trig functions, they might try to trick you in this way, or at least make you think. It's really not, they're not going to trick you, they're going to make you think about it. So just be careful there. Yeah, I like that. Other things we should talk about. Yes. Sure.
It's a linearization
yeah. Oh, yes, I've seen this one.
Roads.
Sure, do you mind if I just grab this?
Yes.
Do you mind? You should have about to drop it, yeah. So let's see here. That. Stay there for a second. Cool. So yeah, this one's not terrible, but it requires a little thing. So here's the situation. We have the diameter of a spherical tumor was measured to be 13 millimeters. So we've got this spherical tumor. And we're measuring the diameter to be 13 millimeters. And then it says the diameter increases by 0.5 millimeters. So if the diameter increases by 0.5 millimeters, use linear approximations, also known as linearizations, to estimate the relative changes in both the volume and surface area. Cool. All right. Let me do this back so I don't break it. Cool. Okay. So here's the idea. When we're talking about, so in that linearization formula that we just did, where L of, yeah, I'll still use X. L of X equals F of A plus F prime of A times X minus A. This part here is kind of like what we estimated the thing to be at the nice value. This is like our estimate of, let's say in this case, of the volume. Or the original volume before we change the radius. So let's say it that way, actually. This is the volume before we increased the radius. Or the diameter, I guess, is the words they actually used. And then this thing over here is our approximation of the change in volume. So when I do these kind of problems, I kind of like to write it this way so that I can kind of see what's going on and say, okay, well, this is kind of the amount I really care about. So the approximate change is going to be your derivative at your nice value multiplied by how much you're changing the input by. So let's take a look here. We know that the volume of a sphere is 4/3 pi r cubed. And I guess I should write V of r here. And our derivative of that, which we're going to need, is 4 pi r squared. All right, the 3's cancel nicely here. So then I know that my radius that I'm going to plug in is half of 13. So at my nice value, my V of 13 millimeters divided by 2 is going to be 4/3 pi times 13/2 cubed. I don't actually really need that. Fine then. So then here's what we would do if we wanted to figure out. So that's kind of what we're saying. When the radius is 13/2, or when the diameter is 13, that's the volume. And then now, if we wanted to find the volume, or I should say, if we wanted to approximate the volume when the radius was 13.5 divided by 2, right? Because we're increasing the diameter, but then we're dividing by 2. So if we want to approximate the volume at a radius of 13.5 millimeters divided by 2, right? We are increasing the diameter by 0.5. Well, that's going to be equal to, approximated by our linearization, which is going to be the nice value we just found right there, our V of 13/2, plus the derivative, which is 4 pi r squared. So 4 pi times our nice, and nice here is really relative, right? 13/2 is not a nice number to be plugging into anything, really, but it's better than 13.5/2. So 13/2 squared times the difference in our variable of interest. So not how much our diameter increased by, but how much our radius increased by. So we're doing R value 13.5 over 2 minus the original A value of 13 over 2. I know it's kind of weird. It'd be nice if you could have reinterpreted this and just said, I'm going to cross this out and say the diameter, nope, let's just say the radius is equal to 13 divided by 2, which is 6.5 millimeters. And the radius is going to increase by half of that, which is 0.25. That would also be a fine way to think of this, because when you do this part here really is just going to be 0.25, because it's 0.5 divided by 2. You can't quite see that. So to answer the question here, the volume is increasing by this much, or I should say, that's our approximation. So this here is approximately, or our estimate of the actual change in volume. But the question didn't ask for that. The question didn't ask us to estimate how much the volume changed. It asked us to estimate the relative change in volume. So relative change in volume, or relative change in something, or relative growth rate, when you kind of slot that word relative in front of the thing, it means instead of giving me the actual number, I want the number you've got divided by the original amount of stuff. So like when it's like the relative growth rate, it's the growth rate divided by the population size. We kind of talked about that before, how if I tell you the population is increasing by 5,000 people per year, it doesn't really mean a whole lot unless you know what the original population was to begin with. So we divide by that to get a more meaningful number. Same idea here. If I tell you the volume increases by 30 cubic meters, well, that's not very meaningful. Was the thing already super big, or was it not? So that's when we talk about the relative growth rate and say, take your change, or your estimate of your change, and divide by the original amount you started with. So here, our actual relative growth rate, relative change in volume, apologies, relative change in volume is going to equal the change in volume divided by the actual volume, which is approximately, well, our change in volume is this gross number here. By the way, there's a reason why I haven't multiplied any of this out, aside from the fact that it's just not nice. 4 pi times 13 over 2 squared times 0.25 divided by the actual volume, which is 4/3 pi times 13 over 2 cubed. And I wish I had more room on this piece of paper, but I don't. But look, things simplify very, very nicely. I can rewrite this as, I'm going to write it all down here again. Delta V over V is approximately 4 pi times 13 over 2 squared times 0.25 divided by 4/3 pi times 13 over 2 cubed. And then you can cancel a 4 here and a 4 here, a pi here and a pi here, a 13 over 2 squared here and a 13 over 2 squared there. And you're left with 0.25 divided by 1/3 times 13 over 2, or 1/4 on top divided by 13/6 on the bottom, which is, I don't know, 1/4 times 6/13. Not the nicest number I've ever seen, but I've seen worse. And that's what, 3/26. Which again, still doesn't feel super meaningful until you write it as a decimal. So if you write it as a decimal, 3 divided by 26 is approximately 0.115, or in other words, 11.5%. Sorry, you cannot see that at all. So what we're saying here is the relative change in volume is about 11.5%. So increasing the radius by 1/4 of a millimeter increased the volume by about 11%, or 11.5%. But you do have to view it as a percentage or as a decimal so that you can kind of think about, right? It's in relationship to the original amount of volume. So saying it increased by relatively by 326 just kind of feels not exactly right to say. It does, I really think you want to think of it as a decimal or a percentage to make it make more sense in your head. And then we can do the same thing for the surface area. So for the surface area, we know that the surface area equation is 4 pi r squared, and the derivative is 8 pi r. So then let's actually skip all the hubbub. That sounded like the oldest thing I've ever said. And say that we're going to do the approximate or the relative change in surface area is just going to be the change in the surface area divided by the actual surface area. But then that's going to be approximately the derivative of the surface area at whatever value we're plugging in for r times the change in r divided by the actual surface area. I'm not plugging in numbers yet because it's inconvenient. So let's just write it out. So that's going to be the derivative 8 pi r times my delta r all over 4 pi r squared. And look, stuff cancels nicely. I should do that. I should have done this first, the last one. And cancel a 4 here and a 4 here, and cancel a pi here and a pi here, cancel an r here and an r here. So then I can say that this is equal to 2 times delta r divided by r. Now I'm going to plug in my r value, which again, they could have picked a nicer number here. We know that the change in the radius was 0.25 millimeters. I don't need the units there. And the actual radius was 13 over 2, or 6.5 millimeters. I should have used fractions. That's 2 times 1/4 over 13 over 2, which is 1/2 times 2 over 13, which is 1/13. Interesting. Again, I don't think that's particularly nice. I would write it as decimal, which is approximately 0.077 or 7.7%. So increasing the radius from 6.5 to 6.75 millimeters increased the volume by about 11.5% and increased the surface area by about 7.7%. And just so you can all see the fun math here that's actually at play, if you think about how much you increase the radius by, the relative change in the radius is the change in the radius divided by the radius, which is 0.25 divided by or 6.5, which should just be half of that, and it is, which is about 0.38, 0.038. But here's what I want you to really see. The change in surface area as a percentage is double the change in the radius as a percentage. And the change in the volume is triple the change in the radius. And that is not a coincidence. It's because the volume is 3 times as dimensional as the radius. And the surface area is 2 times as dimensional as the radius. So the multiplicative difference between the thing you're changing and the thing you're measuring, that error gets propagated that way. So if you're changing the radius 5%, and you're asking how much the volume is going to change by, it's going to be 15%. It's going to be triple, because the radius is dimension 1 and the volume is dimension 3. 1 times 3 gets you 3. Same thing for surface area. Radius is dimension 1, surface area is dimension 2. 1 times 2 gets you 2. And then if you did something silly like change the surface area by so much and ask how the volume changed, you'd have to multiply by 3 halves. Because it's a 3 halves multiplicative factor from dimension 2 to dimension 3. It does totally work. It's just kind of weird. All right, that's all I got.